Alright, so the last couple lessons we've been looking at finding derivatives using first principles, a very tedious process of using the limiting function with our slope, finding the limit of the slope of the secant line as one point approached the point that we wanted to find. But I want to look at some rules for differentiation that make our lives much, much easier. And some of these are kind of common sense, but some of these we'll look at and actually prove a little bit. But you'll notice here we have the notation. We have our original function and then the derivative of that function, and then some of these have names as well. But you'll notice here the derivative of a constant. This one actually just makes sense if you think about it. The derivative gives us the slope of a curve at a specific point. A constant function is simply a horizontal line. Alright, and of course, if you have a horizontal line, which should be straight, a horizontal line has a slope of 0 no matter where you are. So of course, if we have a constant, its slope is going to be 0 no matter what point we're at. Okay, so the derivative of a constant is 0. Then we have x to a power, kind of the basis for all of our polynomial functions. We have this x to the n power. And you'll notice the derivative we will find by taking the original power n. We're going to bring that out in front as the coefficient, and then we are going to subtract 1 from the exponent. Alright, so for example, if we have x to the third power, the derivative of that with respect to x is going to be 3. We'll bring the 3 out in front, and x, and now we subtract 1 from the exponent. So now it's a 3x squared. Then we have two rules that are derived directly from our limit rules. If you recall, the limit as x approaches any value, I won't use c, x approaches some number n, we'll say, of n times a function, is going to equal n times the limit of just the function. Alright, so we were able to take the constant multiple of the function. We were able to take that constant and put it out in front of the limit. Well, because a derivative is just a giant limit, it's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. If for some reason we had multiplied our function by some constant, since this is one big limit, we could factor that constant out like this, and then finally we could take it out in front, c times that, which gives us c times the derivative of the function. Okay? Then likewise we had the derivative of a sum, and an easy way to remember this is that the derivative of a sum of two functions is the sum of the derivatives of those, and that also is derived from the limits, and we're actually going to prove that one here in just a minute. Okay, so let's look at the constant multiple of a function. Using our basic rule of that the derivative with respect to x of x to any power is that power times x to the n minus 1, we know that the derivative of x to the fourth would be 4x to the third. Okay? So, if I have some other function that is 20 times x to the fourth, since I know that, this is just 20 times that original f of x, I could find this by simply taking 20 times the derivative of that original function, that x to the fourth that we saw above. Well, I know that that's 4x cubed, so it's 20 times 4x cubed, which gives me 80x cubed. And of course, as you get the hang of this, this isn't the kind of rule that you're going to write everything out. Eventually you'll just see, oh, 4 times the 20 is 80, and I subtract 1 from the 4, so now it's an x cubed. Okay. The same thing applies here with this 1/2 x to the fourth. I know it's 1/2 times 4x cubed, so 1/2 times 4 is 2, so it's 2x cubed for our derivative on h of x. Alright, so as I said, let's take a look at the derivative of a sum function, okay? If y is the sum of two functions, then show that the derivative of y with respect to x is f prime of x plus g prime of x. Alright, so let's take a quick look at this, and I'm going to start with our first principles here. Any proof of any of these has to start with first principles. So basically what we have here is we're going to have the limit as delta x approaches 0 of our function f of x plus delta x plus g of x plus delta x minus f of x plus g of x. Okay, I'm trying to find the derivative of y, and since y was f of x plus g of x, I've got that as my numerator, and this whole thing is over delta x. Alright, so now what we have is we need to do a little bit of rearranging here. I'm going to distribute this negative to both parts here, and I'm going to rearrange things a little bit. So I have f of x plus delta x, and I have the minus f of x plus g of x plus delta x minus g of x, and again this is all over delta x, and I'm taking the limit of this as delta x approaches 0. Okay, well now I have, you can kind of see this taking shape. Now what I'm going to do is I'm going to split this into two separate fractions. The limit as delta x approaches 0 of f of x plus delta x minus f of x, and that's over delta x, plus g of x plus delta x minus g of x all over delta x. And now we can use one of the properties that we learned earlier, and that is that the limit of a sum is the sum of the limits. So here I have the limit of a sum, so I'm going to change this so it's now the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x plus the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. And now you can see by first principles, this first half here by definition is f prime of x. F prime of x. And this second half here, by definition, by first principles, is g prime of x. Therefore, the derivative of f of x plus g of x is f prime of x plus g prime of x. Now, that may seem a little bit trivial, but the fact of the matter is, without this simple rule, we wouldn't be able to find the derivative of a polynomial like this. Okay, now I'm only going to write it out this way once, but you guys will see the trend here. Alright, so I have this polynomial. I don't have a rule for this entire thing, but I do have a rule for x to the fourth, and I have a rule for something with a constant multiple and an x to the third, so the derivative of 12x to the third, and I can take the derivative of 6x squared, and I can take the derivative of this linear function x, and I can also take the derivative of this constant function, -10. And when I put all this together, the derivative of x to the fourth is 4x cubed. The derivative of 12x cubed is 3 times 12, which is 36. X now is to the second. And notice, since I was adding those two derivatives, I'm going to have addition here. Okay, then I have the derivative of 6x squared. So that would be 6 times 2 is 12, so it's a plus 12. X is now to the first power. Then I have the derivative of x, so here you could think of this one of two ways. Think of it as a polynomial with a degree of 1, so it's 1 times x to the 0 power, and x to the 0 would just be 1, so my derivative is just 1. The other way of thinking of it is to remember that this is a linear function, and slope is constant at any point. Therefore, when we take the derivative of a linear function, we're just going to get the slope. So the slope here is 1. Okay? And then finally, the derivative of -10. The derivative of a constant is 0. So that's why I don't have anything at the end here. Okay? So, kind of doing this a little bit faster as we move forward, we have 1/2 x, or I'm sorry, we have x to the 1/2, so I take the derivative, it's 1/2 x to the 1/2 minus 1, so that's -1/2, plus, I have to do 7/15 times 3, so that's going to be 7/5. X to the 7/15 minus 1 would be a -8/15. Okay, so you can see here, it doesn't matter if they're fractions or even decimals, we just apply the same rule every time. Okay, bring the original exponent out in front as the coefficient and subtract 1 from that exponent. Okay. Now, one last one here. We have to be careful with these because we don't have a rule yet for something where it's a binomial raised to a power. So at this point, what we have to do is we have to FOIL this, x squared plus 6x plus 9. Be very careful to remember to do this. This is a really common mistake. You cannot just put 2 times x plus 3 to the first, because that isn't always going to work. Okay? So now that we FOILed it out, we can say, oh, this is 2x plus 6 plus 0. Alright, so let's do one example here and then we'll let you guys practice with some of these. Okay, we're going to find the gradient function of y equals x squared minus 4 over x, and hence find the gradient of the tangent to the function at the point where x equals 2. Alright, so first of all, the gradient function, that's just find the function dy dx. Alright, and it's going to be in terms of x. So we need to take the derivative of x squared, which of course would be 2x to the first power, but then we need to take the derivative of 4 minus 4 over x. And that's where we may want to rewrite this function as y equals x squared minus 4x to the -1 power. Okay? So we have x to the -1 power. So what we're going to do, we have this minus 4, we're going to multiply by -1, so now it's plus 4, x, and now we subtract 1 from the exponent. So negative 1 minus 1 is a negative 2. Okay? Which, if we wanted to, we could rewrite this as 2x plus 4 over x squared. That is our gradient function. Alright, so now I could plug in any value of x I want, and I would know the slope of this original value, this original function at that point. Okay, so we want the slope when x equals 2, so we're going to take and plug in 2. 2 times 2 plus 4 over 2 squared is 4 plus 4 over 4, which is 1, so that is 5. So we could say f prime of 2, if we were calling this f of x, we could call this f prime of 2 equals 5. And that means the slope of this function at 2 is 5. Okay? So go ahead and try some of the practice that I've given you and see how well you can apply these rules.